living in a country almost swallowed by sandware. More than 95% of the land is desert and rainfall is nearly non-existent. Saudi Arabia has achieved something unimaginable, building a massive steel water delivery system from the Red Sea to sustain the entire nation. Every day, billions of liters of seawater are drawn into large desalination complexes, then pumped across the desert through a pipeline network stretching thousands of kilometers. Bring water inland from the sea is already a remarkable engineering feat, but turning salty seawater into fresh water fit for drinking, farming, and industry is what truly earns Saudi Arabia global respect. So, how is this invisible river of steel built and operated? Join Quantivox Tech as we uncover the answer. Saudi Arabia has more than 37 million people, and almost the entire population follows Islam. What is particularly notable is that most of the population is densely concentrated along the Red Sea coast, and the Persian Gulf remains an almost uninhabited desert. Saudi Arabia possesses what the world desires most: oil, but nature never gives everything. With more than 40 trillion liters of oil beneath its soil, the country still has to spend billions of dollars to produce every single drop of fresh water. Average annual rainfall is below 100 millimeters, while summer temperatures regularly exceed 45 degrees Celsius. To survive under these conditions, Saudi Arabia built a nationwide water pipeline system. The network uses high-strength carbon steel pipes similar to those used in the oil and gas industry. Construction costs average around $3 million per kilometer of pipeline, including booster pumping stations and advanced desalination plants, each of which can cost tens of millions of dollars. But where does this pipeline get its water from? They turn to a nearly inexhaustible source, seawater. However, seawater contains about 35% salt, too salty to drink or use for irrigation. That's why desalination technology was developed. Giving Saudi Arabia a nearly unlimited supply of usable water. The pipeline carries water from giant desalination plants located next to the Red Sea. Each day, such a plant can convert 7 million liters of seawater into drinking water, consuming a huge amount of energy. The first step in building a transnational water pipeline is manufacturing the pipes themselves. Pipes are typically made from high-strength carbon steel, similar to the steel used in oil and gas pipelines, so they can withstand continuous pumping pressure, mechanical impacts during underground installation, and the extreme thermal cycles of the desert. Rectangular steel plates are cut to pre-calculated dimensions sufficient to be rolled into circular pipes with a diameter of about 1.8 meters and a wall thickness of nearly 25 millimeters. She are then fed through a multi-axis rolling machine where rollers gradually bend the steel step by step until the two edges meet, forming a pipe blank ready for the next stage of longitudinal welding. After the welding is completed, pipe is passed through a straight flow water cooling lineado. Reduce the temperature of the weld seam. Next, the steel pipes are carefully ground along all edges, and Cornersto remove burrs and ensure geometric accuracy. Bore further welding, both ends of each pipe are then finished with beveled edge welds, creating optimal contact surfaces for joint connections. Each pipe section is typically about 12 meters long enough to reduce the total number of welds while still remaining practical for transportation. These design allows the pipes to be joined quickly, maintain pressure-tight seals, and remain structurally stable over the long term. When installed along cross-country pipeline route since completed, the steel pipes are moved to an outdoor storage yard where they are stacked by batches and clearly marked for logistics and tracking. From there, they are lifted onto specialized transport vehicles using forklifts or cranes and securely fastened to prevent deformation during transit. Finally, the pipe sections are hauled hundreds of kilometers to the construction site, where they are welded together directly along the cross-country pipeline route. Installation process begins at large staging yards located along the pipeline route. Here, fully manufactured steel pipe sections are grouped by diameter length and installation sequence. Engineering teams carry out final visual inspection, checking pipe straightness, coating condition, and identification. Markings. Proper organization at the staging area is essential to maintain a continuous workflow, minimize delays, and reduce errors when operating in harsh desert conditions. At the same time, survey teams establish the exact pipeline route across the desert using GPS systems, total stations, and terrain data. The alignment is marked directly on the ground with stakes and visible paint. This stage ensures the pipeline follows the most stable and efficient path, avoiding weak soils, shifting sand zones, and areas prone to erosion. For pipelines stretching hundreds of kilometers, accurate routing is critical to long-term structural integrity. Bare trenching begins. Construction site must be cleared and leveled to allow heavy machinery to operate Smooth fly temporary access roads are open parallel to the pipeline to accommodate trucks, excavators, welders, and material transport vehicles in the desert site preparation. Also includes dust control and sand stabilization measures to ensure visibility. And worker safety. This is a fundamental step that ensures the smooth operation of the entire construction process throughout the project. Once the route is finalized, large tract excavators begin digging. The trench along the marked Allen-Menthy Trench is excavated to precise width and depth, allowing enough space for pipe placement. And backfilling excav soil is sorted on site. Vegetable material is retained for backfill, while unsuitable soil is removed, maintaining consistent trench depth and alignment is essential to prevent pipe deformation or misalignment. After installation, in addition, along certain pipeline sections that cross steep and rugged mountain terrain, explosives are used to carve trenches directly into solid rock. Place controlled charge sand, detonate them in sequence to fracture the bedrock along the planned alignment. The resulting blasted trench creates enough depth and width to seat the pipeline securely. Even in areas where mechanical excavation is impossible, this method allows construction to continue through extreme landscapes while keeping the pipeline buried, protected, and structurally stable. After excavation, the pipe is not placed directly onto the trench floor. A layer of selected material, typically fine sand or screened soil, is spread evenly along the bottom to create a bedding layer. This layer distributes loads uniformly and reduces stress concentrations on the pipe. The bedding is leveled and lightly compacted to achieve the required elevation in desert terrain with lucid soils. This step is crucial for long-term stability. To construct large diameter pipeline route, construction quarter approximately 40 meters wide is prepared in advance, allowing the entire installation process to proceed continuously at an average pace of about 1.5 kilometers per day. Pipe sections measuring around 18 meters in length are selected to reduce the number of field welds while also imposing very high demands on lifting, transportation, and precise alignment throughout construction. At the welding site, a hydraulic internal lineup clamp is positioned inside the pipe joint and expanded with 360-degree gripping shoes to hold the two pipe sections perfectly concentric and actually aligned before and during the route pass. An automated welding operation supported by a workforce of roughly 80 personnel and dozens of specialized machines is deployed and can complete up to 150 welds per day on 42-inch diameter pipe. As welding is finished, every joint undergoes automated ultrasonic inspection to ensure there are no internal defects. Field joint coating crew then performs abrasive blasting to clean the surface and applies a multi-component liquid epoxy coating, forming a durable, fully sealed protective layer before the pipes are lowered into the trench and backfilled. Assembled pipes are lowered into the trench using side crane tractor, specialized tracked vehicles designated for constructing large diameter pipelines. Multiple side booms operate in sequence along the pipeline, lifting a section of the pipe string using padded slings and steel cables to protect the coating. Pipe string is raised evenly and held suspended above the ground as the machines move slowly along the trench. Precise coordination between operators is essential to prevent twisting, bending, or contact with trench walls. When aligned correctly, the pipe is lowered gradually in timer by centimeter until it rests at the center of the trench on the prepared bedding route. This process, surveyors continuously monitor pipe elevation, straightens natural curvature to ensure no residual stress is introduced. This method allows fast, controlled, and highly accurate placement, making it ideal for long straight pipeline routes across flat desert terrain. After the pipe is positioned, the trench is backfilled in multiple layers. The initial layer consists of fine material to protect the pipe coating, followed by the previously excavated soil. Each layer is mechanically compacted to achieve the required density, minimizing future settlement in desert conditions where soil structure can be affected by wind and temperature. Extra mass per compaction is critical to pipeline longevity. The process begins by drawing seawater directly from the open ocean and channeling it inland, enabling a steady and uninterrupted supply of raw water for the desalination facility. Large intake lines are first positioned offshore, where installation crews carefully align each section before lowering it into place with heavy lift cranes operating from barges or coastal platforms. As the pipeline extends toward the shore, aligning divil segments are connected sequentially, forming a continuous conduit designed to operate under constant hydraulic load. Precision alignment is critical at this stage, as even minor deviations can affect long-term performance and flow efficiency. Once assembly is complete, the intake line is reinforced with structural support frames and securely anchored to the seabed. The desalination process begins By drawing seawater through pipelines that lead straight into open intake screens, water is pulled from a few hundred meters offshore where barriers and intake filters catch large floating debris and prevent marine life from entering. A 63-centimeter pipe can pull in up to 15 million liters per day. That's more than 10,000 liters per minute. At the intake point, powerful pumps push the seawater toward the plant as the seawater is drawn. In some uninvited guests can show up like jellyfish, crabs, and occasionally small fish. To keep these creatures out of the system, a massive screen is installed to block anything larger than 4-5 millimeters in diameter. After that, the water passes through finer screens to filter out the remaining large particles. Even after the larger organisms have been removed, the water is still full of suspended sediment. Solution is a process called filtration, which takes place in tanks like these. Here, the water flows downward through layers of sand. Using gravity, gaps between the sand grains are so small that only water can pass through, while suspended particles get trapped. Sand continuously moves downward opposite the direction of the water flow, and the dirty particles cling to the sand surface. After this stage, the water looks cleaner, but it still contains countless microscopic particles, anything larger than roughly 1/10 the thickness of a human hair. Remove it next. Large paddles stir the water, and the plant adds to chemical sodium hypochlorite, a disinfectant, and ferric chloride, a coagulant causes the fine sand and waste particles to clump together into larger flocks, which then settle at the bottom of the tank. Most of the dirt has now been removed, but the water is still far from clear enough for the desalination stafford. The water has passed through fine filtration. It enters the cartridge filtration system. Final line of defense before rowing side. Each housing are multiple cartridges made of tightly compressed fiber layers with pore sizes as small as 1 to 5 microns. As the water flows from the outside toward the center of each cartridge, microscopic particles get trapped between the fiber layers, while the clean water passes through the cartridge wall and continues onward. Once a cartridge becomes saturated, engineers remove and replace it to ensure the system always operates at maximum efficiency. Seawater then moves to the most critical stage, separating the salt from the water. Salt is extremely difficult to remove because salt ions cling tightly to water molecules through electrostatic attraction to break this bond. The system must apply extremely high pressure. If water enters a process called reverse osmosis, the real magic happens. The concept is simply pressure greater than natural osmotic pressure, forcing water through an ultrafine row membrane while salt and other impurities are left behind. To generate this pressure, the plant uses high-powered centrifugal pumps. Each component of the pumping system controls a specific pressure stage, with the pressure gradually increasing as the water moves through successive compression phase. B. The time it exits the final stage of the pump, assembled pressure reaches about 60 times atmospheric pressure, strong enough to separate water from salt at the molecular level. After the first round of row filtration, water is already almost salt-free, but it still contains trace ions and microminerals that must be completely removed to meet certain drinking water standards. So the water is sent through a second row stage where even finer membranes operate under lower pressure but achieve higher salt removal efficiency. This stage reduces the water's electrical conductivity to extremely low levels, stripping out the remaining ions and bringing the water to true purified water quality. The final result is an ultra-clean stream of water with near-perfect purity, ready for remineralization or distribution. After passing through the reverse osmosis membrane, purified water is clean enough for irrigation, but it still needs to be balanced before humans can safely drink. To do this, the plant adjusts the usually by adding a small amount of acid or a balancing solution to bring the water back into a safe range. Desalinated water also contains far fewer essential minerals than typical drinking water, so to improve taste and overall quality, a small amount of minerals like calcium and magnesium is added. During the remineralization process, this step restores the water's mineral profile, adjusts the pH, increases alkalinity, and brings back a natural taste, creating water that is not only safe but also healthier and more pleasant for people to drink. And after being desalinated, water is delivered to residential areas through a modern pipeline network to serve the people of Saudi Arabia. However, the cost is extremely high, around $5 per cubic meter of water, something that in the United States may cost only a few tens of cents. So you've learned the whole interesting process. See you in the next videos.